Can you hear me?
Okay.
Okay.
Yeah, I can.
Good evening to everyone. This session will be handled by Dr. Vaibhav Somajianus in the title of Modeling and Simulation of Composites. He has done his PhD in IIT Madras and currently doing his postdoctorate in University of Glasgow, UK. Now session is over to you, sir.
Yeah, thank you. I'll just go to my slides. Can you see my screen? Okay. So, hi everyone, myself Vaibhav, and I am currently working as a research associate in Emerging Space Technology Group in University of Glasgow, that is in UK. And I have completed my PhD in mechanical engineering department. So I had a joint doctoral program with the aerospace department as well. So I was working in aerospace department, but I was registered in mechanical department. So I worked on composites and their experimentations and their modeling and simulations. So this session will just go through some basics, and then probably we can switch over to some of the things that I had done in my PhD. So outline of this presentation would be like this. So we'll start with the introduction. What is a basic, introduction to finite element. Then we'll go to modeling and simulation processes. Then we'll see like two case studies, one of which is riveted lap joint, and another is impact and compression after impact of FR composites. So to start with the basic introduction, like we need to address three problems, like what, why, and how. So we'll start with what is FE. So generally, any mechanical engineer would know like what is finite element, which is we have a bigger structural or any problem that we discretize and we make it small, and we have smaller elements, and those smaller elements, then we analyze those elements, and then we extrapolate our results to the whole system. So why do we need this FEA? Then generally, when we are going for FEA, when we cannot do set of experiments, like suppose we want to go for n number of experiments, and our sample size is very huge, then what we can do is we can just do experiment for few sets, then we can go for finite element, then we can see like how our results are matching with our experiments. And then instead of going for n number of experimental tests, which are generally very costly, time taking, and involves a lot of things, and then results may vary a lot. Like when you start doing experiment in the first phase, and then you at the end of the phase, your results may not converge, or it will be completely different. So instead of doing that, what we can do is we'll do some set of experiments which are very accurate. Then we will go for modeling. Then we'll just correlate both of them, and then instead of going for a set of experiments, then we can just have a model ready, and then we'll just put up a parameters that we want to know, and then we'll get our solutions. So like how do we use finite element? So basically we have a bigger structure, then we discretize it into some elements, then some nodes, and then this entire continuous continuum mechanics problem is divided into a smaller element. And then we have we write some mathematical equations, which are like generally linear algebraic equations, and we predict the behavior of that smaller element, and then we extrapolate that prediction to the entire system. So generally we go for this one for structural finite element for structural analysis, thermal analysis, different types of problems. So I belong to structural analysis, so I'll go ahead with the some basics of structural analysis. So this is like a general modeling and simulation process. So usually, any software package, if you take, like suppose we have ANSYS, then we have LS-DYNA, or we have Abacus. So this is like a general steps that we follow generally in all these softwares. So first we start with this problem definition. So we have one physical problem, and then we want to analyze that physical problem using finite element software package. So let's take example for this. I mean, to understand this process, we'll start with some basic example of a plate with a hole at the center, and this plate is under uniaxial loading, uniaxial tension. Okay, so the first step is to prepare a geometry. So for that, what we can do is we can employ different software, so modeling software such as this SolidWorks, CAD, CATIA, and then using that geometry we can just import that geometry inside this finite element packages, and then we can solve them. Generally, why we do that is because sometimes our geometry is very complex. Like this is a very simple problem, a plate with a hole at center, but sometimes we want to go for geometry which is having a number of nuts and bolts and different complex parts, and they're joined together, and then we want to analyze them. Then it becomes very critical to prepare that geometry into integrated module of any finite element package. So generally nowadays this Abacus and all, it has some good user interface for creating geometries, but still it's better to go for dedicated softwares which allows us to have multiple I mean ready-made models of this nuts and bolts and all these things available, and that we can use straight away, and then we can create a geometry, and then we can import using some suitable importing some. So basically we can use integrated model as well. So this is like this geometry is particularly created in a integrated model of ANSYS. So here is just like this problem is we have axisymmetric problem, so we will just prepare a geometry in only in one quadrant of this plate with a hole. So generally I was doing a problem with a hole at center, and then we had a different functionally graded material rings around that hole, so we can minimize the stress concentration. So this is just example of that. So what comes next is material properties. So what we do is when like after defining the geometry, then we have a module of material properties. It's in general in any software packages. So where we define our different material properties such as your modulus, then we have Poisson's ratio, then we have some fracture energies, strength parameters, then some interfacial properties. There are multiple n number of properties that we need to define. So that depends on a problem actually. So if we are going for some isotropic materials, then we just need to give some moduli and some Poisson's ratio and some fracture energies. But if you are going for some orthotropic material problems, then we need to define a number of material properties. Like we have, I mean you must be knowing that we have generalized Hooke's law, so it has almost 81 material constants, and then we reduce it to some 2 to 3 for isotropic. So that many parameters we need to define in general. So then we have our we have to define our material model. So this particular is Johnson's Cook material model that we use for metals. Then generally in software packages, when we define any geometry or when we define a problem at the beginning, that itself considers its material model. But if you want to go for some specific material model, like we want to have a user subroutines, then we can we can define our own material models, and then we can integrate that material model into our software packages. For that, we need to have you need to write some codes in some different language such as Fortran and everything. Then once you write those codes, then you can integrate your material model into that software packages, or else you can just use some predefined material models inside the software packages, such as this model. And for composites, we use hash and damage. So then we go for some governing laws for material properties. So suppose we want to vary the material property in particular direction. Suppose our we want to vary the property in let's say in length direction. So we will have some variation laws. So those laws we need to take care. So once we define all these material properties and material models, then we allocate those properties to particular material components. Suppose this is like a isotropic plate here. Just a second, let me start. Yeah. So suppose this is a problem of some isotropy, but if we are considering that these plates which are joined together are of different material, then we assign different material properties to different section of that geometry. And then comes the meshing. So once our geometry, our material properties, everything is ready, then we go for discretize our entire geometry into some smaller elements. So here what we do is we create some nodal points on this surface. I mean, on the outer, circumference of this geometry. I mean, that depends. If you want to go for free mesh, then you can go for free mesh as well. But if you want to control your mesh, then you probably go for controlled mesh, where you can give a number of seeds, number of elements, and number of your nodes. And in that sense, you can just define your mesh. Why it is important to control mesh quality or your mesh size is because if we want to have our solution converged, then it's better to control your mesh prehand. Like once you solve your problem, sometimes your problem solution doesn't converge. That is because your mesh quality is not good. So for that, generally what we do is we go for some meshing strategy, we call it. So for that, we'll go for some different energy based meshing strategy, and then we have some strength based meshing strategy. What we do here is we just give some properties to those equations, and from that we just derive one a parameter called characteristics length, and based on that we decide like what should be the minimum mesh size, so that our solution solution is converging. So that helps in both ways actually. So that helps in converging your solution as well as reducing your computational time. So generally we go for meshing strategy, as well as if you want to have a better mesh, then you can employ some meshing softwares as well. So it's not like you can just mesh in your own integrated module of suppose ANSYS or Abacus. You can employ some different meshing softwares as well. So for meshing, generally in ANSYS, for this problem particularly, we have different elements, where we have link element, beam element. For 2D problems, we have plane, shell elements. Then for 3D problems, we have solid 45. Then we have brick elements. Then some cylindrical elements as well. So the different types of elements are there. Then those elements, depending upon their properties and depending upon your problem, then you can give type of element to that particular problem. Then comes our loading and boundary conditions. So here, like in this particular problem, we are going for uniaxial tension. So what we are going to do is we are going to give tensile load on this particular end, and we're going to fix this end, and there is a hole at center. So these are based on your whatever physical problem you have defined. Based on those problems, you just define your loading conditions and boundary conditions. So these values you can just give it into the model. Like suppose you want to give a load of 1 kilonewton, then you can just give it to 1 kilonewton, or you can define it as a pressure, or you can define it as a stress, or you can define it as a displacement, or there are a number of loads as well. So you can give it as a displacement load, or some force or some pressure, or some a number of loads are there. So for some fluid problems, for thermal problems, you can give temperatures, like multiple types of loads. And then you define your boundary conditions where you have you are fixing one end, or you are allowing the degrees of freedom in x direction, y direction, or in this problem we are allowing x1 or x2, and then you are restricting in x3, or if you have dimension x3 dimension, or you're not allowing in negative x2, like particular in particular direction, if you're not allowing this plate to move, depending upon your problem definition, you can just give your boundary conditions and loading conditions. And then comes the part of solution, post-processing, visualization, and validation. So like once you're done with all your modules, like problem definition, then your geometry preparation, then your material properties, meshing, loading, and boundary conditions, then you just solve this problem. And once once your solution is converged, depending upon your solution is converging, like based on your meshing strategy and everything, then you go for post-processing. In post-processing, what you do is you just evaluate different types of stresses, then you go for strains, displacements. Then if you want to have particular stress component, like one meso stress, or you want to have you want to see the stress variation in x direction, y direction, those particulars you just find out in post-processing. Sometimes you don't need displacement, so unnecessarily you just if you're calculating displacement, so you are increasing your computational time. So whatever you need, you just evaluate those things only. And then comes visualization. So once you are done with your evaluations, then you can just plot your contours. Then you can plot your graphs, like how the stress is varying around the circumference, and how the stress is, like suppose you have calculated sigma x, then you need to know like how your plate is behaving. Then you have some stress concentration, like in general, if you have uniaxial tension, then around hole, these are the locations you will generally encounter the stress concentration. So this is how you visualize the problem. And then comes the part of validation. So generally, why we do validation is we don't know whether we have solved correct problem, or we have whatever methodology we have followed has given us correct results. So what we do is generally uh, uh, I mean in general, what method we follow is we have one predefined solved problem in any literature. We just try to solve that problem initially. Then we try to put our things, our parameters in that particular problem, and then we solve it. And then we see like how both things are matching, are not matching, how it is behaving. Or the validation can be done in other way also. There we can just do some experiments, and then we do some modeling, and then we validate both the things. So you can do validation in different types, so that depending upon your problem. So let's start with our first case study. So where we have a riveted lap joint. So this problem defined as a, like suppose we have any aerospace structure where we see in general this riveted lap joint. So this geometry has three equally spaced rows of countersunk rivets. So here three rivets, and this is a replica of these threes, and totally we have nine rivets. So this is total length is some 362, then overlap is of 74 then we have 72 width, and this is like outer sheet, and this is like an inner sheet, and the two are overlap. They have overlap of 74 And then comes our material properties, as we discussed earlier. So we have our material properties. We have, these are the sheets of aluminum generally used in aerospace structures, any aerospace structures. So this is like this is the grade of aluminum that is being used. So we have material properties such as Young's modulus and then Poisson's ratio. For rivets also, we have these countersunk rivets with the diameter of 5 and these are the properties for those particular rivets. Then we actually, what I was doing with this problem is we wanted to have wanted to see like if we have conventional riveted lap joint, and the stress concentration that is happening around the rivet holes, can we reduce those stress concentrations? So what we did is we employed some material gradation into around that rivet holes. So that was the problem I was actually addressing. So what we did is we created a geometry in SolidWorks of that particular riveted lap joint, where then again we went for assembly of this FGM rings, this particular functionally graded material rings. These are generally uh, like I'll just explain what is FGM. It is like a material which has a smooth gradient from one material end to other. Suppose we have an interface, and in that interface we like there is a sudden change of properties, then there is a huge rise in stress concentration. So we want to reduce that stress concentration. What we can do is we can employ some gradation in the material at that particular phase, and we can have smooth transition of material from one material to another material, and we can reduce the stress concentration. So that is the concept behind this FGM. So what we did is we assembled multiple FGM rings inside those rivet holes, and then we again had a rivets, and then we had a lap and everything. So then this is our free mesh model. Initially we went with the free mesh model, and later we employed our controlled mesh as well. So these are the loading conditions and boundary conditions. We just wanted to go for uniaxial tension, like, because there are different n number of components involved. We just wanted to see like how it is behaving under uniaxial tension. And after that, we saw like this is our visualization and validation part. So where we saw like how this for conventional lap joints, we saw this inside inner plate we have some riveted lap joints where we are getting 164 MPa of stress concentration happening at these particular points. And once we introduced our FGM rings, entire like full FGM rings inside those rivet holes, like if we could, instead of going for separate rings, we can just go for a full ring, and then we can press a rivet. And then we saw there is a reduction in stress that is concentrated at these particular points of these contact surfaces. And again, once like if you want to reduce it further, then we can just go in a different separate FGM rings around rivet holes. Like for top plate, some different like outer plate, and for inner plate, different rings, and we can have further reduction. But this is much complex. It is not possible in a you can put different holes in different, I mean different rings in different holes, so it becomes very critical. So just for future perspectives. So our second case study is impact and compression after impact of FRP composites. So I don't know if I mean maybe many of you might be knowing like what is composite materials. These we'll just go through some basics. So this is like a class of advanced material which is made up of one or more material combined with a distinct physical and chemical properties, but they still act as a single entity. They are being used in different applications in like aerospace, automotives, naval applications, because they have high strength to weight ratio, high stiffness to weight ratio, and they're corrosive mainly because they have because of their this strength to weight ratio and high stiffness to weight ratio. And apart from that, they provide better corrosive corrosion resistivity and fatigue. These are different applications which includes this satellite structures, aerofoil surfaces, some mud guards, door panels, in sports as well, some tennis rackets and fishing rods, etc. So let's define our problem. The problem we are addressing here is, once these composite materials are employed in a real-time application such as your windmills and your aerospace structures, they are always subjected to some or other type of impacts. So like for this one, this is like a Boeing 787 Dreamliner. It is made up of more than 50% of advanced composites. So here it is like there is a particular study we have seen. It shows there is 265 incidents of impact related damages on that particular structures in a span of 39 months. So what happens is its structural integrity gets degraded, and once it is degraded, then its effect is very dramatic. I mean dramatic effects. It can have very dramatic effects. It may fail at any point, or I mean it's very important to have a structural health monitoring of such structures. Even for this windmill blades, we have some bird strikes and some drone strikes, and then we have some hail and rain and some snow particles and all those dust particles. Multiple a number of things are there, which are because of that what we are having what we are facing is this barely visible indentations, like a debris impact on a aerospace structure. It cannot be seen with the naked eye. So I mean, we don't know it is present there, but its effect on structure could be very fatal. So we want to address these low velocity impacts, and then we want to see like how this damaged structure is behaving under compressive loads. Most of the structures generally put into compression loads, different types of loads, but we are addressing the problem of compression. So the thing is, just a second, yeah, experimental methodology for some amplitude data. So what here we did is we went for validation of this our simulation with our experimental data, and what we did is we did experiments. We collected some amplitude data such as velocity amplitudes, then we have displacement amplitudes, and a number of amplitudes, and then those data we fed to our model, and then we generated results, and then we matched both the results that we generated from simulations, and then we had it from experiments, and then we correlated those those two different results. So here this was our testing setup for impact. So instead of going for some hypothetical impacts, we created indentation on a specimen. So this is a carbon fiber composite laminate that we created some quantifiable impact. That is we went for different energies like 10, 15, 20, 25 joule of energy impact on the particular composite material, and those specimens we again went for testing inside the UTM for the compression. Yeah, so this is a if you see here, this is our low velocity impact test that is being captured in a high speed camera at 6000 fps, and then we simulated same into the abacus. So here what we did is we created a geometry, and we created an impactor, sorry, which is rigid impactor, and then we assigned properties to that particular impactor. Like if you want to give it a velocity, then we have a velocity amplitude. Then if you want to give displacement, then we have a displacement amplitude. So a number of things we can these are just input parameters, and this is our boundary conditions for those that particular low velocity impact test, where we have a rigid frame, and there is opening of some. This is like a 150. The specimen size is 150 by 100, and there is opening of 100 by 75 inside that rigid frame, so that we can create a impact damage without any baseline support. And then we went for compression after impact. So here what we did, the same specimen we put for the compression test, where this is like a CAI this one support fixture that has been given in the ASTM standards. So that we prepared in like one of our workshop facilities, and what we did is these particular platens here, they avoid global buckling of the specimen, and they just ensures that this specimen is under pure compression. So these are the real-time conditions that we want to analyze, and we want to have pure compressive behavior of this damaged structure. So we don't want any buckling to be happening at this particular this test, because what we are going to do is we are going to give similar boundary conditions to our simulation problem. So we don't want any buckling that is happening at this experiments. So here we have this to calculate the strains, we attach some strain gauges, and we got some strains as well. And yeah, again we went for some the whole contour of like suppose we have impacted damaged specimen, and the impact is happening at a center, and what ASTM suggests is we calculate strains at these particular locations, because once you have damaged your structure, you cannot attach a strain gauge at that particular point, because that particular point no longer is flat, and you cannot attach your strain gauge there properly. So instead of calculating strains at these points, they just ask us to calculate at these particular points. The problem with this is we just know the strains at those particular points. If you want to know like how the strains are spread over the entire face of the impacted structure, then it's better to go for this DIC. So what it does is, what we do in this DIC is we just capture our entire experiments in the n number of frames, and then we just use this VIC software where we just load the speckle images, and then that speckle, that software, what it does is it captures a particular movement of this particular points on that face, and then it just creates contours of strains and displacements, and I mean in the background, so that we can generate those contours, we can generate later. So yeah, so this is our simulation of low velocity after compression after impact test. So once we have our damaged specimen, then we just remove all its boundary conditions and loading conditions, and we remove this as well, our impact and everything, and then we the same like LVA, like impact damaged specimen, then we fed it our next step for this compression after impact tests. So once we have this set, this both simulation data, then we can correlate those data with our experiments. Yeah, so this is for a DIC study. So as I said, it's like a instead of getting some localized strains, we can just get a strains over the entire face of the specimen. Like suppose this is the impacted specimen, and we expected it to fail at this particular point at this center, because it has been impacted, and we know that there might be some stress concentration that are happening here, and that's why it's going to fail there. So what we do is we just record this entire our test of compression, and then those speckle images, we just feed it to our algorithm, and then it gives us strains that are spread over the entire face of the specimen. So like once we have our geometry, our problem definition, everything is ready with us. So what we do is now we define our material. So first, like for one part I did was carbon fiber composite laminates. So we had 12 different specimens. So what we did is we just the stacking sequences of this particular specimens, we just switch its places, and then we had a number of different specimen with the different stacking sequences, and the material is this one, it's CU403 unidation carbon, and then we have epoxy L/556 as our matrix material, and then we had hardener of this one. And our specimen is, we define a geometry of 150 by 100 mm. That is according to our ASTM. Then we I mean, we don't know like how much thickness for each lamina. Like suppose we have 0, 45, 90, minus 45, and that particular geometry we want to create in a suppose in a abacus, then we need to know like what is the thickness of each lamina. Then what we do is we calculate the thickness of each lamina by theoretical calculations. Like for this particular material, what would be the thickness of lamina, and that particular thickness we give it to our model. And this material properties that are being provided, some material properties being provided by manufacturer, some we get it from some literature or something. And we have different material properties such as elastic properties that are like modulized. And for strength we have different tensile strength, compressive strength, shear strengths. Then for fractures we have toughness, fracture toughness. Then that those factors, toughness under tension, compression, then transfer tension. So shear, fracture toughness. So these are like n number of material properties that we require for this particular problem. And then we have interfacial properties because we like like we have different laminas that are being assembled together to form a single laminate. So we need to give interfacial properties because they're going to have interfacial I mean, with one lamina to another lamina there will be some behavior at the interface. So we need to define those properties as well. And then we go for meshing of our problem. So what we do is we generally where after like meshing strategy we come up with a some particular characteristic element length, and then we define element sizes which are lower than that element size characteristic length. And generally at the center, like where we are impacting our specimen, that particular location we give a little fine mesh because I mean that depends on your requirement for the solution. So generally why we do it is we will have some fine results at that particular location because this particular location is going to degrade a lot. Then we like from the experiments we get some results for this with a force time history, that is for the impact behavior. And for compression after impact we get some results for experiments like stress time curves. So what we like for this particular problem, what we have seen is there is a reduction in strength of the compressive strength of the material. And here like our material model, our sorry, our FEA model and our experiments that are not completely matching, but there is some 10 to 5 to 10% error. But still our maximum values are within range, like 5% error. So maybe that is because of some experimental error, but that we can eliminate by refining your experiments. But that is again it's I mean depends on your expertise or your experience in that particular experiments. So like as we go into doing all these experiments again and again, and you'll just get good experimental results. But this was just for initial part. So uh, what we did is we just validated our results with our experiments in this particular thing. And yeah, so this is for the simulation part. So this is our specimen 0, 45, 90, minus 45. So these are like some important failures in the that are happening in a impact of composite laminate. So for like if you see this is like a 8 different laminas stacked together, and then we generated results at each lamina for this particular failure mode, that is fiber tensile failure mode. So when impact is happening, this is like a top layer and this is like a bottom layer. So the impact is happening on this particular layer at the center, and we see there is a failure of fibers, which is oriented in 0 degree. So that particular information our model is capturing very accurately. Here we have the orientation in 45, and then we have in 90, and then in minus 45. So what interesting is that our model is capturing information accurately, and it is giving like another good information that the failure that is happening during our experiment is also limited to top 4 layers for this particular failure mode, tensile failure mode of the fibers, because there are a number of failure modes. Like there will be some matrix failure, then there will be some delamination failures. So for this particular failure, model is capturing good correlation with our experimental results that we can see through again we have some ultrasonication methods, and then we have X-ray methods, and then we can that I will show in few slides. So this is a fiber compressive failure mode during impact test. So here we see the fibers are getting compressed only under the impactor. So that particular failure is not spread over the length of the fibers. It is just right under the impactor on the specimen, and it is not propagating until the end. It is just for the first few layers it is more prominent. And this is another important failure mode, fiber compressive failure during compression test. So what happens is, like if we have a lamina joined together of n number of lamina, suppose we have 8 different layers that are joined together, what happens is this top layer and bottom layer, they're because they are away from the mid plane, their stability is inherently very low. And once we impact it, once we create an impact damage on those particular laminates, their stability again degrades. So what happens is those particular laminates during compression, they again go under huge compression failure, rather compared to other this inside laminates. And then we have matrix compression failure, which is again prominent failure, because for compression tests, for any in general compression that is happening during impact or that is happening during particular compression strength like isostatic compression, matrix material is the main material which is taking most of the load for this particular composite materials. So if we are going for tensile tests, then fibers will take most of the loads. But for compression, it will this matrix material will take most of the loads. For that, this failure criteria is like very, very important. So here also we see there's a prominent failure of this matrix compression under impactor on the top 2 or 3 layers, but particularly on top layer it is more prominent. And again, during compression tests, matrix failure is like spread across the entire laminate, because that is the main material that is taking up the load. Yeah, so I was telling what we can do is we can just go for this non-destructive evaluation using X-ray CT scans. What we do is here we know what is the thickness of each lamina. Then what we do is we just do some X-ray scanning of that particular laminate for different thicknesses, and then we generate surfaces at different thicknesses throughout the entire thickness of specimen, and that those surfaces are generated at the lamina thickness, and then we generate like we get to know what is the different failure modes happening at that particular laminate. So we have this is a different problem actually, where we had glass fibers as well. So we had different orientation of fibers where we have 0, 90, then minus 45, 45, like those orientations we could see in this X-ray scans, and then we'll get to know what is the different failure modes that are happening on the inside the material. And this is for the compression after impact, where we see like this is the impacted face and this is the back face. when we created impact on the this composite laminate, that it propagated as a delamination to the back face, and once we load that particular into compressive loading conditions, there we see that delamination has become has given rise to more delamination, and there will be some ply splitting, different types of failure modes that are happening. Then yeah, so what we did is we yeah, in cross section also we saw like how this ply splitting and everything is happening. This is like impact phase, this is the back phase, and those results we correlated with our model. And then we could see there's a good correlation with the experimental results and our finite element model. And again, for this some micro failures, we went for SEM analysis, where we see like how this is happening, like that comes in a validation part, like why the particular component is failing, that where we have fiber rupture and then fiber matrix debonding, then we have some shear failure zones. And so there will be some a number of failures that are happening in a entire laminate. And then that's it, like we have completed our validation. So yeah, so these are some references that used for this particular presentation. So thank you very much for this opportunity. And if you have any questions, like you can just ask.
Any questions from offline participants? Any questions from offline participants? Okay, so I have a few questions.
Yeah, please.
So it is possible to find out fiber pull out through simulation?
Yeah, it is possible. So during my actually for my master's project, I did fiber pull out test through this one, ANSYS as well. So where we need to know, we can evaluate our interfacial shear strengths and those particular problems. And then what you usually do is, for that one, we have this is like a cylindrical problem. So you just need to have a representative volume element, where you have a volume of matrix, and then you have volume of fiber, single fiber, and then you just load that single fiber over this this surface at one end. You can just load the fiber. Then you need to give interfacial properties, like I've shown in this one. Some interfacial properties will be there, and yeah, you can simulate that fiber pull out test in a ANSYS, or you can do it in Abacus as well.
So you have made the composites with different from play angle, right? So have you used hand layout technique or compression molding techniques, sir?
Generally, what we did is we go for hand layup and then we go for compression molding.
Okay.
So I mean, I prepared a number of samples for. So you can go for different methods. You can go for vacuum bagging as well. Then you can go for some hand layup and then compression molding. Then you can go for your we have a machine of this one also. This huge pressure chamber. I forgot its name, but there are a number of methods by which you can just But for this one, and this particular what I've shown here, we did it with the hand layup, and then we went for compression molding.
Because my intention is want to know the defects present over there if you're going for hand layup techniques such as porosity or improper filling due to the resin curing time, etc. That's what I want to check it out, whether it's correlated with the premature failure. Here you can clearly show that delamination of the fiber is also shown. I think everything is covered. You covered.
Yeah. So generally, I mean, porosity or some this air pockets inside the composite laminates is very common problem that is that everybody faces. For that, what you can do is you can employ some methods such as some vacuum bagging, or you can go for some sort of vacuum generation where you just remove all the air pockets, air bubbles in the uncured matrix itself. So instead of going for laminate and then you removing all those things, and while doing hand layup or all those things, you can remove all these air pockets and everything during your matrix phase itself before mixing the hardener with it. So you just go for some vacuum assisted air bubble removal.
Okay,
So
sir.
that those type of things you can think of for this one, but that is in general everybody faces that problem. So here also, if you see here, I could see, I will show you just like. Yeah, see, these are some words. These are unavoidable.
Yes, sir.
I
Yes,
mean,
sir.
yeah.
One of the difficult challenges we're facing with simulation in composites, but
Yeah.
somehow you have cleared and you got
Yeah,
nice work.
that's what we try to do maximum what we can do, but again we will end up with some microwatt we'll end up with. So there is no that's why we have some experimental error as well, 5 to 10% or something.
Okay, sir. This is what from offline participant. And now some of the online participants, they have raised their queries in the chat box. If it is possible, could you go to the chat box and give some solution for that?
Just a second, I will go.
Yes, sir. Or else can I summarize that, sir?
No, I cannot see anything
Okay.
written in the chat box.
Okay, there is one small question. It is asked by Shankar Kumar, Satish Kumar something. So, what is this question means? Through experimental, we can able to find stress strain, and he want to know how to find out the other properties or how to calculate.
So basically, what we do is he's asking from experiments, right?
Yes, sir.
Yeah. So generally, we go for material characterization for n number of tests. So this is like a series of tests that gives us material properties, and those material properties are generally our tensile strength. Then we have compressive strength. Then we have fracture energies. Then for those properties, you go for again this one 3-point bending test. Then you have 4-point bending test. Then you have DMAs, and you have DSEs, and n number of different experimental methodologies you have to characterize any material. So that depends on, like, suppose you want to have you want to go for a thermal analysis, then you need to have all the its conductance, and then its I mean different material properties. You go for a different set of experiments. Then like suppose you want to analyze you have a fluid problem, then you go for its viscosity, and those tests are set up in ASTM standards, and then you go for those particular tests, and you evaluate all those properties.
Okay, sir. So one more question. What are the properties required during ANSYS simulation? Because in Abagus, we may directly enter the true stress strain curve as Poisson ratio directly we can enter. So he's asking what are the properties if you're going for ANSYS.
Yeah, even for ANSYS as well, you can give like you are going for a structural analysis. Then you may, like, if it is a isotropic problem, then you can go for straight away. You can give moduli, and you can give Poisson's ratio. And for orthotropic problems, you give properties in X, Y, Z direction, and then I mean it is this material properties module is same for all the this one all modeling and simulation software. So this material model that contains this particular any problem, any structural problem, for that structural problem we need to give all these material properties, no, modulize, and Poisson's ratio, and other like fracture properties and all this. So there will be one module in the ANSYS as well for these material parameters input.
I think this is all about the session, sir. So you have clearly given a solution to the offline as well as online participants' queries. So I think we can wind up the session now. I'm handing over to Dr. Naveen.
Okay.
Thank you, Dr. Vaibhav, for joining
Yes.
from Glasgow, explaining in detail.
Yeah.
Thank you for the wonderful session.
Yes. No issues. Thank you.
Thank you. We can
Yeah.
log off. Thank you.